Finally, we're now able to revisit our initial model. Remember, we got two events, ML out, ML in, and also we got the two invariant conditions. Accordingly, we got four different sequences representing the proof obligation related to invariant preservation. Can we discharge them all? In which case, we can declare that our initial model as is actually correct with respect to invariant preservation. If we fail any of the proofs, in that case, we may have to fix the model and then reattempt the proof to make sure we can discharge all the proof obligation. So that'll be the flow for this final part of this week. Let's take a look. I'm going to switch to iPad, but I would suggest don't look at the slide just yet, because the slide only contains the solution for the proofs. I would suggest let's go for the step very quickly. So I already got two things over here. You can see this part here. I got all the four sequence over here, right? You can see for ML out and also for ML in. In the case of a ML out and ML in, we had to prove invariant condition number 1. And for ML out, ML in, we also need to prove invariant condition number 2, right? We got 2 times 2 sequence to really discharge. That's what we want to do, right? We already did one of them, if you recall. This one was already done, right? And just recall very quickly, that one there we simply try to do monotonicity over there, and in which case we can simply disregard certain hypothesis. So the only thing that's left is n is a member of the natural number, and turnstile n plus 1 is a member of a natural number. And this sequence over here that's being transformed into matches the Peano theorem. Which one? Well, you can see it should be number 2 over here, right? N plus 1 is a natural number. In that case, assuming that n is a natural number, in that case it can be proved without any justification, right? So by Peano theorem number 2, in that case we are able to discharge it, right? Very quick review about what we did earlier. What about the remaining 3 proof obligation? Right, let's do one by one. I'll definitely give you a chance to pause the video and attempt it. Right, don't worry too much if you really have no idea. At least you give it a try. Right, even if you really applying inference rule and somehow leading you to nowhere, that's okay. At least give it a try. All right. Let's now do. How about this? We already did invariant number 1 for ML out. Why don't we do the same invariant but for ML in? The only difference is you can see the guard is still true, well, as is, but the action is going to be n minus 1, right? That's the before after predicates. Okay, why don't we try this one here? You can now pause the video and think about it. All right, assuming that you thought about it. So if you look at all the inference rules over here, it seems to be the only thing that will actually work is really to, well, think about what's happening here. The OR inference rule wouldn't work because that require either the hypothesis or the either the hypothesis or the goal for the sequence should really contain some disjunction. But that's not the case for any of these, right? There's no disjunction over here. So the OR inference rule wouldn't apply. And also for the increments over here wouldn't apply either, right? You can Peano theorem, nothing we can use because those rules require the antecedent to be absent. But that's not the case for us. The only thing that we can apply will be the monotonicity. That's the only one. So we're going to drop some hypothesis. But what should we drop? Since we are now talking about n minus 1 is a natural number, so we should definitely assume something that's relevant to n. And so that seems to be the only one to say n is a natural number, right? N less than or equal to d is only about its upper bound, but now we are decrementing, so it wouldn't help, right? So we can definitely first, the only option we have is to apply the monotonicity inference rule, which is going to transform this sequence into, we're gonna drop all the hypotheses. We're gonna drop all the hypotheses except for n is a natural number, right? Similar to how we did it for this one here. Let's see if we are lucky to reach something that without any further justification. N minus 1 is a member of the natural number. Okay, once we get to here, can we claim that we are done? Have we got a proof? Well, it seems like we cannot, because you can see here, this part over here is really n minus 1, right? Do we have any n minus 1 in the inference room? We do have n minus 1 over here, but remember here n minus 1 is under the assumption that n should be positive. But here we say n is actually a natural number over here, right? If n is a natural number, that means n might be 0, in which case n minus 1 will not be a natural number anymore. That'll be minus 1, right? So basically we're stuck, all right? So I'm just going to follow the textbook notation. We're going to put a question mark over here, right? That means we fail to complete the proof over here. That means it's not really a theorem, this sequence over here. Because somehow, once we drop the irrelevant hypothesis, whatever that's left as the hypothesis is not strong enough for us to really prove that the goal is the case. This might be a good indication that we might need an extra guard for the events to say that you should not be able to do n minus 1 always. You may only do n minus 1 when other conditions are true, right? That's something we'll get into, right? At least you should understand. This is the only option we can take to begin with, number 1. Number 2, once we did it, we have nowhere to continue. Just not possible, all right? All right, so that's about the failing proof for this particular proof obligation for MLN related to invariant condition number 1, right? Why don't we try this one over here? So that's going to be about invariant condition number 2, which is the new value of n prime should be less than or equal to d, right? But now n prime has been replaced by n plus 1 in the case of m out, right? All right, you can now pause the video and try it. All right, assuming that you thought about it, and it's going to be a very similar idea. In this case, the only thing we can use at the moment as a first step will be the monotonicity. You can definitely rewind to see why I justify why this will be the only rule we can apply to begin with. Similar idea, right? Let's now try that. So monotonicity over here. Monotonicity, and what should we drop? We should really drop anything that's not relevant to the n plus 1 over here, right? So maybe what we can keep is, except for these two, because since you are trying to add 1 to n with respect to d, so we should really find the hypothesis that's relevant to n and also d, right? So this might be the one we want to keep, right? So let's now put it. So it's going to be n less than or equal to d, and assuming that it is the case, can we prove n plus 1 less than or equal to d, right? So that will be the transformed sequence over here. Do we have a proof? Well, let's take a look. So here we say n plus 1 less than or equal to d. The only thing that's kind of close for us is something like here, right? You can see the increments over here. n plus 1 less than or equal to something. However, it's only given the assumption that n is strictly less than n. However, what we got is n is less than or equal to d, right? It's not exactly matching. So we cannot apply the increment rule. We just cannot, right? Hopefully you're following me, right? So it seems like we're stuck, all right? We don't have a proof. We fail, right? So far we failed to proof obligation, because somehow the antecedents of the hypothesis over here that's actually too weak. It needs to be stronger by adding maybe some extra guards to ML out and also ML in. ML out to ML in. All right. Finally, let's now consider the proof for this. Okay, and you can now pause the video and think about it. All right. Assuming that you thought about it, first of all, do we have a proof? Well, actually we do have this proof obligation. Let's see. This one will be kind of interesting to see, right? Again, the first step we should really apply following the same justification will be monotonicity. Okay, so I'm going to do that. Monotonicity over here. Right, since now we're talking about n minus 1, and also, well, similar idea, right? We want to actually somehow to say n minus 1 less than or equal to d, and also n less than or equal to d. So I think these two are relevant, right? And these two are just the typing for the variable, which are kind of implicit, we can assume, all right? So what we got is, over here, n less than or equal to d, and then n minus 1 less than or equal to d. Right? So that's the sequence that's being transformed into. Do we have a proof? Well, basically we are talking about n minus, well, actually, you see, we're getting very close to the decrement rule. If you notice that, right? You can see here, if you look at that, let me just show to you. If you look at the n less than or equal to d over here, n less than or equal to d is really matching the n less than or equal to n over here. However, the n minus 1 less than or equal to d is not really matching n minus 1 strictly less than n. It's not really matching, right? You can see, so we cannot really apply decrements rule directly. So if you simply say decrements over here, it would be wrong. All right. So make sure you understand why we cannot apply that just yet, right? But what we can do is we can do a little bit of manipulation, right? So let me just put back the box over here, right? What we can do is somehow think about what's really saying over here. This over here. This n minus 1 less than or equal to d really means n minus 1 is either less than or equal to. If we somehow can really get to the less than part, in that case, it would be matching this less than part over here for the decrement rule, if you see what I mean over here. But how can we get there, right? Two things. One thing I would like to do implicitly, which you also show in the textbook, right? This part here, we can just rewrite it without justifying it. This is rather basic. But of course, you got to show the step. So this is really equivalent to n minus 1 is less than d, or n minus 1 is equal to d. Do you agree? Over here. Right? Less than or equal to can be split into either less than or equal to over here. And what can we do to really somehow only consider just one of them? Well, it sounds like we do have something here, right? We can choose to only consider the left disjunct over here. If the goal is actually a disjunction over here, we can choose to drop the right disjunct over here. Drop Q and only keep the P, right? So that's what we're going to do. So let me write it down. So we're going to get the rule, which would be the OR over here. And again, the R over here simply means we are talking about what's to the right of the turnstile, right? And then we got R1. You got to write down the name correctly, right? Once we do that, we can actually got something like this: n less than or equal to d. Okay, sorry. N less than or equal to d, turnstile, and we only keep the left disjunct over here. That's the only thing we keep, which will be n minus 1 less than d. Now, do we have a proof? It looks very, very promising because let's now compare side by side. If you look at n minus 1 less than d, that one nicely corresponds to n minus 1 less than n. And for the hypothesis, n less than or equal to d correctly nicely matches n less than or equal to n, right? So we basically, you can think about the n in the rule is corresponding to d in our sequence, right? So by the rule of decrements, we do have a proof. Decrements. Right? So we should really say conclusion. We check. This is proved. This is also proved. But too bad, we actually got two outstanding sequences that failed to be proved, right? And the reason that they cannot be proved is actually because we actually got the hypothesis that's simply too weak, and that's something we'd like to fix, right? Let me go back to the slides over here, and then let's see how we can fix it, okay? And the two slides over here are exactly the proofs which I just went over with you, right? The 4 verification conditions which we did, right? So you can definitely go over that. They have been discussed already. Let's now move on to how we can fix the model. The way to fix it is really to say we don't really want these two events, right? You can see these are the two verification conditions or proof obligation that actually failed to prove if they fail because the events are enabled when they should not be, right? If you look at the failing proof over here, you can see, for example, here the n-1 is actually executed always without any guard. So that means you cannot say if n is a natural number, then n-1 is always a natural number. When n happen to be 0, you just cannot really do decrements. And similarly, when n is equal to d, you just cannot do n plus 1. Otherwise, you will just exceed the limits, right? That'll be the insight you should really have, right? Having this feedback, so now we can add the 2 guards into our events, right? So this will be the revised model. You can see the update, the action itself, it doesn't really change. These are the good actions, but we want to make sure the actions are guarded. They are conditional. We are only going to increment the n, the variable n, when n currently is strictly less than d, meaning that we don't have that many cards yet in the island bridge compound. And also we're going to do n-1 when n is larger than 0, meaning that we shouldn't really allow any card to really go into the mainland when the island bridge compound actually currently got 0 card, right? Something it should be there should be at least 1 card in the compound. Otherwise, how can the card actually go from the compound to the mainland, right? Right. So that's the fix we did. So these are the only 2 things. I'm gonna highlight them when I show you the regenerated proof obligation. But now you want to understand very clearly about the picture. Having changed both events by adding the guards to them, they should be updated sequence that should be regenerated. Of course, usually the generation process will be automatic, but of course you should also know how to generate them manually, which I'll show to you, right? And so now for invariant preservation, we still have 4 proof obligation, 4 sequence, because we still got 2 events and 2 invariant conditions. And are they now provable? That's the question, right? So we're going to go over them, right? So that'll be the contents for the next 2 slides, but I'm going to do it again on the iPad for completeness, right? So let's now switch to this regenerated sequence, right? The naming convention is still the same as before. We still got ML out, MLN, MLN, the 2 events. For each individual event, we got invariant 1, invariant 2 for ML out. And also we got invariant 1, invariant 2 for MLN. So now the difference is, let me highlight to you exactly the difference in the model. For ML out, we have added this particular guard. And for MLN, we have added this particular guard and this particular guard. They used to be true, so they could be disregarded. But now, if you remember, I think it's really important for me to show you very quickly, right? If you remember the rule about invariant preservation over here that we spoke about earlier, the guard of the events that we are considering should be included, right? So that's why they are there. All right, let me go back. It's really important for you to understand every step, right? And we used to be able to prove this one here and this one here. I can tell you that they should still be provable in the revised model just by adding the extra guard. Because when you actually apply the monotonicity, you can still just drop the guard if you don't think that's relevant. So the proving process will be just the same, right? So I can tell you that they are going to be discharged. This will be okay, and this will be okay as well. So I'm going to leave that as an exercise for you. Okay, so there'll be exercise to prove it. And I'm going to do the other 2. Okay, so this will be discharged, and this will be discharged as well. Okay, you can do it. They should be rather straightforward, right? Let's now do these 2 that used to fail on the original model when we didn't have the guards, right? Let's take a look how we can prove them. Can we start with this first? All right, so it's gonna be invariant condition number 1 for MLN. All right, you can now pause the video and think about it and do it. All right, assuming that you thought about it, of course we're gonna apply monotonicity, right? That's the only one that can allow us to drop the irrelevant hypothesis. So what should we keep? We definitely want to keep this new guard. That will be very valuable, and also we want to keep this guy over here as well, right? So we want to make sure, oh, actually, sorry, not this one here. Since we talk about decrements, right? And also, I think that'll be it. That'll be enough, right? So for the typing constraint, that will be implicit assumption. So you don't really need to include it over here. Because when you say n is larger than 0, you're basically saying that not only that it's a natural number, but it's also positive, right? Right, so let's now apply monotonicity. So we're gonna drop 1, 2, and 3, right? We're gonna drop this set of predicates as the hypothesis. So what we have is we got n larger than 0 entails n minus 1 natural number. Now, do we have a proof? Well, is there any inference rule that represents an axiom that can be applied? Indeed. If you look at, how about this one here? Piano rule number 2, prime. We're saying that n minus 1 would be a natural number, assuming that n is a positive number, n larger than 0. So this one's matching, right? So now by P2 prime, we have a proof. So P2 prime, that'll be okay, right? Right, so this one is proved. Awesome. And we got one more. How about this one over here? Alright, so this one will be ML out with its new guard with respect to invariant condition number 2. Right, you can now pause the video and try the proof. Alrighty, assuming they thought about it, let's do this final exercise for the week. We're still going to apply monotonicity, right? But what should we keep in this case? Well, we definitely want to keep this new guard. That'll be very useful, right? So n is less than d. You can see this one logically is stronger than this, which is good, because now if we get this, in that case we're basically done. But you gotta make sure you drop all the irrelevant hypotheses first. We can drop the typing constraint. We can drop this, which is weaker than this, right? So what we got is we can have n less than d, the new guard, yields or entails n plus 1 less than or equal to d, over here. And let's now put it into the box over here. And do we have a proof? Well, it looks like we do. And which inference rule can we apply? Well, you can take a look at over here. What about the increment over here? Right? You can see that's exactly right. Okay, let's just see the connection here. N less than d nicely correspond to n less than n over here. N plus 1 less than or equal to d nicely correspond to n plus 1 less than or equal to n. It's just that d has been replaced by n. Well, sorry, n has been instantiated by d in this case, right? We're instantiating the rule. Right, so we do have a proof. In that case, we can simply put increments. And we're done. Alright, so the conclusion is by adding the 2 guards to really revise the model, we are now able to actually discharge all the full proof obligation. So what's our conclusion? Our conclusion is our model, so the conclusion is really important. So we want to understand why we're doing all these, right? So the conclusion is M0 as is after the fix is correct. However, we're going to say with respect to, we're going to be precise. It may not be correct just yet for other criteria, but at least for invariant preservation. Because we have discharged all the proof of all the sequence generated by the invariant preservation proof obligation. Preservation. It's a very important conclusion you should really know, right? Conclusion, and then is correct with respect to invariant preservation, right? That's a conclusion for us. Let's go back. Right, so if you go over the next 2 slides, exactly what I just showed on the iPad, all right? Alrighty, and I think this week is definitely heavier than last week in terms of the technical content, because last week was mainly just to explain some background and also introduce you to the problem for the bridge controller. But this week we really dive deeply into the idea about how you can formulate your proof obligation, how you can systematically generate different sequence, and also how you can discharge or prove each sequence that's outstanding into ones that are actually provable without any further justification using inference rule. You want to make sure you really understand all the tiny bits for this week. I try to be very thorough and complete. Hopefully that really helps. Alright, so that's about it for this week. I think we're just about running out of time. And next week, we're going to continue with our initial model, but with other proof obligation.